Now we're going to look at section 17.4 and 17.5. If you recall from last semester, we looked at electrophilic addition to alkenes. If you recall, when we have an unsymmetric alkene, okay, the first step is addition of H plus, and then we're going to make a carbocation. If you recall, we're going to form the more substituted carbocation. Because this is more stable. In the last part, to complete the reaction, the Br minus adds to the carbocation, and we get our alkyl halide. Now what we're going to do is we're going to look at this reaction with conjugated dienes. And because we have two double bonds, we can get a mixture of products. And we are going to see that the major product strongly depends on the temperature of the reaction. So I'll just draw the overall reaction of 1,3-butadiene with HBr and then the two products that we get. Right, so there are two products, and what you'll see at negative 78 degrees Celsius, we'll have 90% of this alkyl halide and only 10% here. And if we increase the temperature to negative 15 degrees, we can shift that balance. Alright, so we need to understand why this happens. And then we're going to use this to predict the major products of electrophilic addition to conjugated dienes. We have two double bonds. We can have two possible carbocations. We need to follow this golden rule. Always make the resonance stabilized carbocation. Okay, if you always follow this rule, you will not go wrong. Okay, so let's look at how to do this. We have our 1,3-butadiene. We add HBr. The first step is to make the carbocation. So we have, let me number, 2, 3, 4. This is just for bookkeeping purposes. 1, 2, 3, 4. So we can either put the carbocation on carbon 2 or I have an extra carbon. Carbon 1. Now I told you our golden rule. We always have to make the resonance stabilized carbocation. So we will not make this carbocation. The first one is resonance stabilized. Right? So these are the two carbocations that we are going to work with. The next step is for Br minus to add to the carbocation. Now, if the Br minus adds to carbon 2, we get the 1,2 product. If the Br minus adds to carbon 4, we get the 1,4 product. So here are our two alkene products. Now what we're going to do is we're going to evaluate how we can shift the equilibrium to favor one over the other when we change the temperature. So I showed you before that the ratio of the two products depends strongly on the temperature. When low temperature is used, the reaction is under kinetic control. And what this means is the kinetic product is the product that's formed the fastest. When we have high temperature, the reaction is said to be under thermodynamic control. And the thermodynamic product is the most stable final product. I'm going to underline final. So, when you are looking for the kinetic product, you are going to look at the intermediates to decide. You're going to look at the carbocations. When you are determining the thermodynamic product, you are going to see which final product is the most stable. Okay. So I'm going to rewrite the intermediates and the products up top here so we can see how this works. Okay, so we have our two carbocations, and we have our two products. Now, if we look at the intermediates, here we have an allylic secondary carbocation, and here we have an allylic primary carbocation. The allylic secondary carbocation is more stable. What this means is that the actual structure of the carbocation, you're going to have a larger partial positive on carbon 2. I'll number them again. 1, 2, 3, 4. You have a larger partial positive on carbon 2 than you do on carbon 4. 2, 3, 4. So when Br minus approaches, it's going to see a larger positive charge at the secondary carbon, or carbon 2 in this case. Because it sees a larger positive charge on the secondary carbon, it will react faster at this position. That is why this makes 3-bromo-1-butene (3-bromo-1-butene). Now, if we were to raise the temperature, the reaction is going to become reversible. The reaction is reversible because there's sufficient thermal energy to allow breakage of this carbon-bromine bond that was formed in the second step of the reaction. So now the kinetic product can convert back to the carbocation, which can then react again with bromide. Now initially, most of the product will again be 3-bromo-1-butene, but we will start getting some 1-bromo-2-butene because we do have some of this cation present. Now that we can continuously break this major product up because we have enough thermal energy, what will happen is that the more stable alkene, the 1-bromo-2-butene, will begin to accumulate, and it's going to shift the equilibrium to favor this more stable alkene. The alkene is more stable because it has two substituents on it, whereas this alkene in 3-bromo-1-butene only has one substituent. This more stable product is lower in energy and is less likely to go back to the carbocation. So over time, more of the thermodynamic product is formed at the expense of the kinetic product. This is why a higher temperature favors formation of 1-bromo-2-butene, while lower temperature favors 3-bromo-1-butene. And I'll show you the energy diagram to illustrate this. Alright, so if we look at this energy diagram, you'll see here we have 1,3-butadiene in HBr. We form one intermediate. This intermediate is going to have both carbocations in resonance with each other. As such. What this means is that these two structures represent this one intermediate. There will be a greater amount of positive charge here on carbon 2 because that would be a secondary allylic, as opposed to here where you would have a primary allylic. Here we have our two products. Here we have our thermodynamic product, and we have our kinetic product. Now I said the kinetic product is going to form the fastest because it comes from this more stable carbocation, and there's a larger partial positive on carbon 2 of the intermediate than carbon 4. The thermodynamic product is the more substituted alkene. It's more stable. It has a higher activation energy for formation, but as we raise the temperature, we can overcome this barrier and we can form the thermodynamic product at the expense of the kinetic product. Alright, now we're going to look at the case when we have an unsymmetric diene. So we have two different double bonds here. Okay, so if we have HBr, and we add to the double bond that I have drawn, we're going to draw the resonance stabilized carbocation. See its resonance structure. It would be that cation there. Right now when Br minus adds, we have two products. Now let's work with the other double bond. Again, we draw the resonance stabilized carbocation. And then its resonance structure. And then we can have Br minus add to both. So as you can see, we have four different products here. And we need to evaluate what will be the thermodynamic product, and what will be the kinetic product. Okay. Let's label our intermediates because we're also going, and our reactants, because we're also going to translate this into an energy diagram. Okay, so I'm going to call this A, this intermediate B, the two products that come from B, C and D. Okay, again, this is reactant A. This will be intermediate E, and the two products that come from E will be F and G. Now, let's start with the thermodynamic product. The thermodynamic product has to be the most stable alkene. So we need to look for the most substituted alkene. So here we have three substituents. Here we have two. Here we have one. And here we have two. So now we know that product C is the most stable product. Okay, so this is our thermodynamic product. when we look for the kinetic product, we have to work within the carbocations that led to product C. So the kinetic product has to be product D. Okay. Now, and if we look at the carbocations from intermediate B, we'll see here we have a secondary allylic, and here we have a tertiary allylic. Right, so the thermodynamic and the kinetic are going to come from the same intermediate. So product D will form the fastest at low temperature, and product C will be favored at high temperature. And I will draw an energy diagram on the next slide to show you what this looks like. Okay. So here we have energy. Here we have the reaction coordinate. This time what we're going to do is we're going to put A, which was our diene, and the HBr in the middle. And we're going to go to the left, and we're going to go to the right. Okay, so as I said before, if we looked at the products, we would see that B, intermediate B, is lower in energy than intermediate E. We also know that product C is the lowest in energy. Okay, and then we have product D. Now G has the same relative energy as D because they are both disubstituted alkenes, and F is the least stable because it is a monosubstituted alkene. Okay, so let's connect everything up. It's going to take a higher activation energy to get to C than it will to D, and then it's going to take a higher activation energy to get to G than it will to get to F. So this is how you would make an energy diagram for an unsymmetric diene.